Welcome everyone to Resilient Energy Design. Thank you for joining us today. This webinar is brought to you by Second Nature in partnership with Eaton. This webinar will be recorded, and the recording and slides will be sent to all registrants in the days following the webinar. There will be a Q&A session at the end, and you can submit questions for the Q&A at any time using the questions function on your GoToWebinar panel. Next slide, please. Second Nature would like to thank our corporate sponsors for making this broadcast possible. Thank you. Next slide. I just wanted to take a very brief moment at the beginning of the webinar to go over the climate leadership commitments, as they're still new, and many of you attending today are probably new signatories of either the climate commitment or the resilience commitment. Second Nature has recently updated and relaunched all of our commitments. Many of you are familiar with the ACU-PCC. So signatories of the carbon commitment who were signatories of the ACU-PCC and are focused exclusively on mitigation are now signatories of the carbon commitment. People who were signatories of the ACU-PCC, if they would like to start working on issues regarding resilience as well as mitigation, they can opt into the climate commitment and focus on both resilience and mitigation at the same time. Excuse me. Or a new campus joining today that has previously not been part of the climate leadership commitments in the past can choose any one of the three commitments to focus on, either resilience exclusively, mitigation and carbon neutrality exclusively, or both combined together in the climate commitment. Next slide, please. And the reason that we updated the commitments and relaunched them this fall was that it's increasingly becoming important that leading on the issue of climate change is not just mitigating, but also having the capacity to respond and adapt to the changes that we're already experiencing. So some of our key goals for the commitments were to really focus on the idea of proactive management and responding to risks and opportunities ahead of time, and really having a lot of integrated planning around the issues of climate change. And we also wanted to emphasize the connection of higher ed to the community and in other sectors outside of higher education. So we've tried to really build that connection into the new commitments. Next slide, please. So they do have a common framework, though, as you can see here, and most importantly, the Sustainability Planning and Climate Action Guide. That is a big component of that idea of integrated planning that we're talking about. So that is an online interactive resource for implementing any of the commitments, and it really breaks things out in terms of some of the building blocks you need to sort of organize your campus to get ready to make these activities, to organize your staff and external partners. And then there are several chapters of building blocks about mitigation and resilience and academics and financing and different tools to help you implement the commitments. Next slide, please. And some of our goals around the resilience commitment, obviously with the climate commitment and the carbon commitment, the focus there is on carbon neutrality, so there's a clearly defined goal. With resilience, that's a little bit more challenging. What do we say when we're committing our campus to resilience? So we needed to sort of develop a definition of resilience to help people understand what it was that they were trying to achieve by signing the commitments. And one of the things we did when creating that definition was to make it positive, proactive, and looking to a positive version of the future. So that we didn't just focus on reducing vulnerability or surviving intense storms or severe climate disruptions, but also thinking about the abilities to anticipate, adapt, and flourish in the face of climate change. And then you can see there's some additional goals which are very similar to the goals for the commitments in general, which I already talked about. Again, this idea of connecting to the community, of proactive integrated planning. Next slide, please. And when implementing the resilience commitment, some of the key concepts to focus on when we're thinking about how we define resilience or how we achieve that, again, is sort of partnership with the community. And again, that idea of proactive integrated planning where we sort of assess, understand, plan, and measure indicators of success. But we also try to think about both adaptive capacity and better adapted infrastructure. So adapted capacity might be something that enhances your ability to respond to changes, no matter what those changes might be. It might be having financial reserves. It might be having a very highly educated population that's able to deal with change. And a better adapted infrastructure, a lot of the traditional things we think about of having proper storm barriers that can withstand the anticipated storm surges in the future, more resilient infrastructure around energy systems like we'll be talking about today, etc. So we try to think about both of those areas of resilience. Next slide, please. So today's webinar is the third in a series of webinars that we've been giving. You can view the first two in the series on our YouTube channel and download the slides from either of those. And today we're covering the last in the series of resilient energy design. Next slide, please. So I would just like to introduce our two speakers. Gabriel Paletti is the Eaton Application Engineering Manager, and his focus and expertise is a lot around electrical power distribution and design, installation, commissioning, upgrading. So we welcome Gabe, and we are looking forward to hearing his presentation. And our second speaker, next slide please, is Justin Karen. Justin is the Global Segment Manager for Healthcare and Universities at Eaton, and his expertise and background is in finance and economics. So we welcome our two speakers, and we really look forward to hearing their presentations. And again, just to remind everyone, you can ask questions with the questions function in your GoToMeeting toolbar, and we'll have some questions and answers with our speakers at the end of their presentation. And with that, I'll turn it over to Gabe and Justin.
Yep, thank you. This is Gabe Paletti. I'm going to be talking about energy resiliency, microgrids, a number of topics, and they are linked to climate leadership from the standpoint that, if you're planning to do some renewables in the future, or fuel cells, or more and more options are coming about, battery storage. One good thing to consider is if you have a control system now and it's antiquated, if you update that control system, you would want to make sure it's something that you can then later scale it up and bolt on modules to allow the inclusion of these other sources to help with climate leadership. So that's just kind of a little bit of a linkage. So next slide, please. And again, like mentioned, all the material is available. This is just a quick little history. Thomas Edison started up basically effectively a microgrid in New York City in 1882. It took a lot of work. He had to get approvals from lots of different government officials. If you see in the 80s, now keep in mind in the early days, this was not regulated. So little companies were coming up and generating their own power, building their own power plant, running their own lines. You literally had competing electrical lines. Finally, in 1895, Westinghouse received the order to build a large power plant in Niagara Falls. This was shifting also to AC power. Early on, Edison was promoting DC power. AC power, basically, you can transmit further. So as technology grew, the generating systems got bigger. When the Great Depression hit, there was a fellow named Samuel Insull. He actually worked for GE, then realized the money to be made was in owning a generating plant and selling electricity. So he was very proactive. He went out to Chicago, built a bunch of plants, bought out the small plants, had things like time of use metering, had demand charges, was actually starting to supply power to rural customers. But one of the things he realized was that he had to negotiate, like Thomas Edison did in New York City. He had to negotiate with every little town to run his wires, to connect to customers. So he took the initiative and pushed that regulation, lobbied and pushed it up to the state level. So that was a big step change because Then once there was the Depression, he had so many companies, he was convicted of fraud. It's really a kind of a sad story for somebody who did so much for the electrical industry. But after that, and then when you get up to the 30s, now it became fully regulated. You know, every state by then had regulated. And keep in mind, at that point, you have nuclear technology. So what you have is basically massing of power generation sources at large single sites versus a bunch of small sites like you see in the upper left. So by 78, we have a fully, you know, regulated kind of utility industry. Next slide. Yeah, so basically, but you know, when you have such a big interconnected grid, there's been some major blackouts, and they average about every 10 years. So in 1965, a relay didn't operate, 30 million people affected. There was one in New York City in 77, in 2003, another blackout, another 50 million people. And there are increasingly grid outages. Now, this has nothing to do with storms, has nothing to do specifically with aging infrastructure. It's primarily such a big interconnected grid now. It's almost too big and almost too interconnected, so that if something malfunctions, things got to operate. But I can tell you the utilities are upgrading their protection and control systems very rapidly because of, you know, a lot of systems are literally 30 or 40 years old. Next slide. And then you have issues like storms that occurred on the East Coast that generated a lot of funding for things like community microgrids, where universities were encouraged to, you know, connect with a local hospital or a local police station to create a community microgrid, and they even offered funding. New York State offered $100,000 to 83 different groups to just do a feasibility study. So storms played a role, and cybersecurity is becoming a bigger and bigger issue. You know, there's people hacking into you know, utilities. Next slide. And if you look at our grid in general, you know, so the other issue too is with renewables. You know, renewables are excellent. They help with climate leadership, but as things progress, people start to realize there's new issues arise. So if you see in the upper right, that's a profile of solar power, and when the cloud cover comes over, that represents a 10-minute gap, where if you had, you know, 30% of your power being supplied by solar, all of a sudden you don't have enough power. So, and what's happening on the utility side is utilities are being forced to create a certain amount of renewables, which is a good thing. But now they have, if they get close to 10-15% of their power generation is coming from renewables, it's not as stable as a large rotating generator that's got all this inertia built in and isn't going to stop turning pretty much, you know, except for an outage. So what they're finding they need is they have to add battery storage to supplement for the wind dropping or the solar disappearing because of cloud cover. And, you know, at the bottom just shows some of the challenges with wind power. Next slide. Yeah, so again, and we just jump right to the next slide here. Yeah, so what you have is a number of factors. You know, on the West Coast, they put in so many renewables, they need to beef up their resiliency by a combination of battery storage, microgrids, just to kind of deal with the fact that the generating source is no longer a big, massive facility sitting in one place. So that's in the center of the country. You have a lot of retiring plants. All the coal plants are being shut down. Some of them are being converted to other sources. But in general, you know, that's lost generation. So either they build another plant, or they go to, you know, universities, hospitals, schools, and say, hey, can you beef up your own generation capacity or your own renewables at your site? Obviously, we have the storms going on, and again, in the Northeast, there's been a strong push. New York State's effectively coming out soon at some point with regulations that are going to entice and motivate a university, for instance, to connect to the grid, and when they don't need their backup generator, sell that power to the grid and earn revenue. So all the other states are watching New York to see how they come out with that. So there's lots of factors affecting the resiliency. And again, cybersecurity is kind of one floating about. Next slide. Yeah, so as far as microgrids, historically power flowed in one direction, flowed from the generating plant to your laboratory or your classrooms, and then you see in the upper right, there's lots of information on microgrids. A simplified one is, you've got some solar, some wind, generator, some battery backup, and you've got your loads, but that controller is the important piece in the pie, because that's what's going to control and maximize your energy savings, your resiliency, your climate, keeping down your carbon footprint. So that controller, it's probably 8 to 10% of the price of all those assets, but it's the most important piece. And then Sandia National Labs, they've actually started to define things like a basically local microgrid all the way out to a substation microgrid. Next slide. So there's lots of activity going on. The Navy's implemented what's called a green microgrid, where they basically do some energy savings. Next slide. And you see there's a map of a number of microgrids. This shows a power line, literally about a quarter mile from my home. And one thing you can see here is the grid is somewhat vulnerable. A lot of people have these power lines. If two or three of these went down, there'd be an issue. Interesting story. I was going to San Francisco to present at a conference, a similar presentation to this. I'm on the flight. I decided to watch an old movie because it was free. It's the movie where they break into the casinos in Vegas, and they actually show a diagram in the movie of knocking out 3 or 4 of these towers in a row, and it blacks out Las Vegas. So there's lots of potential resiliency issues that we never really had before. Next slide. Yeah, so this just gives you a feel for the Department of Energy is tracking microgrids, at least at government facilities and different locations. Next slide. So you see there is a lot of activity already going on. This quickly shows how California, I mentioned, is requiring battery storage of 1.3 gigawatts of installed battery backup by 2020. Hawaii has some requirements. There's another item called frequency regulation you see in the Texas area and the Mid-Atlantic area. What that means is the utilities have these large generators, and they're spinning, and they're turning a generator. They're burning, either oil or fuel or nuclear. So they're turning, and but since they don't have as many generators, when all of a sudden the generator does drop out, what happens is the frequency slows down, which means instead of you receiving 60 cycles on your AC line, you might be receiving 59.8, 59.7, 59.6. Well, it turns out operating those large, massive generators at anything below about 59.6 shortens the life of those generators. So the utilities now, because they have aging plants that have been shut down, they need to put in battery storage on the East Coast and in the central U.S. to back up the power when a power plant goes down. And like I mentioned, New York, it's called the Reforming the Energy Vision, REV. You can look it up where they're coming out with regulations to help everybody become a generator of power and contribute to a truly distributed grid rather than these central large plants. Next slide. Yeah, so we just go right to the next slide here. So this is what usually the features exist. So there's a system design, making sure it's integrated with your existing assets, and then you always want to make sure you're putting in a system though that's scalable. You don't want to have 2 or 3 different controllers because it's just they may not talk to each other with the proper protocol. So it's good to get a system that you can grow with. Seamless islanding means you completely island from the grid. And there's some large facilities that do this today. They completely, or they're off the grid. They're not connected to the utility. Now that doesn't mean they're not using natural gas though. Black start means you can actually start up with no external power. That's not as easy as it sounds. Even generating plants have external power that comes in to help them start up. But that's a feature that's got to be part of your solution. Frequency and voltage control, I kind of talked a little bit about that. System balance is the idea of also having a system that can shed certain loads, things that don't need to be on in a critical situation, those things would automatically get disconnected. And then renewable optimization is that piece which is really not so much university-based, but up at the utility area space where they need to now optimize all these renewables they've got connected to the grid because they're not as stable as the traditional power generation. And then lowering costs, there's lots of opportunities to shave your peak demand, some peak shaving on your utility bill. Next slide. Yeah, so the bottom just shows what a typical system looks like that would be scalable. So for instance, you'd have a controller that would control a fuel cell and a separate one controlling an engine generator, another one controlling battery, another one controlling solar, another one to the far right would be shutting loads off. They would all connect to a master controller that would connect to the utility. So the idea is you want to, if you're replacing, if you look at the second one, engine generator, say you've got some old generator controls. Well, if you're replacing those controls today, you want to make sure you're putting in a system that can then be built upon and communicate to these other systems so that you can, kind of take advantage of future options to give you that climate leadership and that smaller carbon footprint. Next slide. Yeah, this again just shows how things can be packaged. So, the one big, that everything shown in the green there can be, can be purchased as one system, or just one of those systems can be purchased. Next slide. Yeah, this is the example where you're starting off with just one controller, but it's again, it's scalable. It's already ready to be interconnected to other future controllers and has that capability built in. Yeah, next slide. Yeah, this shows kind of a picture of what the hardware looks like, and it's like any electronic equipment. There's lots of wires. There's certain standards. IEC 61850 is basically a standard that makes sure these devices can talk to each other and they're not left hanging out. You want to have, if you're buying a system, you want to have a small UPS, uninterruptible power supply, to make sure the controls work no matter whether the power goes on or off. And so that little box to the upper left actually shows 6 local controllers that are controlling local devices. And then there's the second row's got some switches, that are, allowing those controllers to talk to each other. Then there's a larger controller followed by the UPS. And it's nice to have things that are, iPad accessible and controllable. Next slide. Yeah, this shows an example at MIT. They have a Lincoln lab where they actually encourage customers to come in and they simulate your controls to verify they operate. So they had a conference, about 150 people. We were there. Our controller worked really well. If you look to the left, what that screen to the left, what they do is simulate the solar coming and then disappearing. That's the lower blue graph there that all of a sudden dips. And then they watch our controller start generator 1, but that's not enough power. So our controller starts generator 2. That's not enough power. Now we start some battery backup to get back up to the load requirements. And then when things drop down, we recharge the battery. So it's interesting. They allow people to simulate their controllers. And if you're in the, obviously, and there's a large lab in Sandia. So there's probably there's probably 2 or 3 major labs. Eaton we have our own lab. We have 2 of them, one in Menominee Falls, Wisconsin, and one in Pittsburgh, Pennsylvania, where we simulate our own because, if you're creating a product, you need to have your own simulation. Next slide. Yeah, so basically the key point is the controller in the center is what's controlling all these different assets. So that's where you want to make sure it's scalable, it's reliable. The products we use actually the hardware has been used in the utility industry for over 20 years. Next slide. And it's already cybersecurity hardened and those kind of things. Yeah, next slide. So some of the other big assets involved, though, is bidirectional inverters. Next slide. Basically, this is something that's taking the power and it's sending it to batteries, but then once you need that power, it takes the power from the batteries and sends it back. So if you look in the lower left, the new units are very efficient over a wide range of power. Now again, this is a case where you're putting in batteries or solar, because batteries and solar are basically creating DC, and you need, primarily you need AC. Now there are some people looking at putting in DC distribution systems within their facility, feeding right off of the DC generated to certain loads. LED lighting can actually operate off of DC power. Next slide. Yeah, this just shows the variability too you have with these inverters. You control your sine wave, you control the frequency. You basically have a very sophisticated electronic device giving you the perfect sine wave that you need. Next slide. Yeah, this is an example, Portland General Electric, and again, you can maybe even Second Nature can put a link to the website. If you go to our website, you'll see the video, but if you go to the next slide, this is an interesting example of a community microgrid where Portland General Electric, we work with them, and they basically connected a group of customers together and put in some. If you look at the lower left, that's the substation that connects to the rest of the utility distribution network, and you see it says 1.3 megawatt hours of energy storage. So they put some batteries there. And then the yellow line shows basically a dedicated kind of little microgrid connecting different customers. There's a hospital, a data center, a food plant that makes food. So now what they're able to do with our controls is everybody can benefit from each other's backup power. So if someone needs generation and one of their diesels go down, they just actually, boom, hit a few buttons, and now and now everybody's, so you're basically gaining resiliency from the standpoint that you're all connected together, and you kind of can work with each other and help each other out. And they have a nice video that describes this on the website, and again, we have a link to it. Next slide. This just shows what's at each of those locations. So there's a data center, there's a food plant again, and what kind of generators exist at those different, and then there's batteries at the utility substation. Next slide. Yeah, this again is just more details. There was batteries installed. We provided 20 inverters. We provided the low voltage, and then the key part was that networking. That control framework that allowed all these different assets at these different locations to work together. Next slide. Yeah, so some of the things we were able to seamless transition from the utilities to battery. We did dynamic load sharing between the 20 different inverters. We tested these lithium-ion batteries with rapid charge discharge cycles, because there's a lot of data out there on batteries, and that's one area though. The battery companies, what they'll give you is they'll say, okay, here's the discharge, here's how many charges and discharges you can get at a full discharge. But in a lot of these situations, you're not doing a full discharge and charge. You're doing maybe a 20% discharge or a 5% discharge. So the question is now, what's the life of that battery at 20% charges and discharges versus 100%? They all have very detailed testing on full discharges. They'll tell you can do this 5,000 times. But what if you're only going to do a 20% discharge? Do I get 7,000, or maybe does only doing a 20% discharge limit me to 3,000? So there's lots of still questions, but there's a lot of good work being done on the battery side to help promote. So there's different batteries basically. If you're going to have short discharges, there's different battery technologies better than if you're anticipating larger discharges. And this is where things like a feasibility study are obviously good to do. Like I mentioned, New York State funded 83 feasibility studies for about 100,000. You can probably get a feasibility study done for 10 or 15,000 for a university, maybe 20. But what it involves is looking at your loads, looking at your existing generating sources, then looking at what can be added and what's the most economical way to add some sort of renewable energy or alternate energy, or build, adding onto an existing CHP or building on a CHP. Next slide. Yeah, this just shows an example of how the inverter is responding to differences in signals from the outside. So the inverter outputs at the bottom, that goes up and down, and it's basically offsetting the load going up and down so that everything stays the same. So you can have all these different inverters in this case operating independently, but they're still all talking to the controller, and they're taking their generation source and feeding it into the kind of community or little subset microgrid. Next slide. This is an example of frequency regulation. So when you lose the generating source, but the load's still connected, it's literally going to slow down these rotating devices a little bit, because it's kind of like you have a rotating fan and you grab hold of the little plastic fan, obviously. But I mean, if you grab hold of something that's spinning, you're going to slow it down. So that's what happens without the generating capacity that used to exist. Again, shutting down the coal plants, retiring nuclear plants. We just don't have these big rotating generators spinning with all that iron and mass and weight behind them. So when that frequency slows down, it's damaging the existing generators. It really doesn't impact the customer a whole lot. It would mean if you had a clock that was running off that frequency, the clock's going to run a little slower. Probably you would never notice it. But this shows the difference of having these very fast inverters responding very quickly to limit. So you see, we would have went down to 55 hertz, but we're only going down to 58 hertz. It doesn't sound like a whole lot to you, but actually it's a lot when it comes to the electrical side. Next slide. Yeah, so again, there's a video available that you can go, and we have a link to it. Next slide on our site, and maybe again Second Nature can link to it. We've done a lot of work with the government over 10 years. We've 10 years of experience on microgrids. The government's very involved. We've done everything from putting in a microgrid at Fort Sill, which is the picture in the lower right. They actually simulate. They actually have a windmill, solar. They have diesel generators, natural gas generators. So they wanted to make sure the control system could operate all these different devices. So then that allows them to deploy it. If you look in the second picture on the left, that's actually a microgrid. It looks like a bunch of brown boxes with wires. That's actually a microgrid for a forward operating base. It turns out when the government, the Army, or the service is being dispatched, obviously they need power, and they traditionally brought diesel generators. So you're running these diesel generators. So what our microgrid, basically a small kind of full operating base type microgrid, what it did is it didn't allow all the generators to run. It just ran the generators they needed based on the load. They used to just run the generators. The payback in those systems for the Army was like 3 days, something like that. It was amazing. But again, in their situation, they can't be worried about fuel sometimes. But it still was a great savings for them. So we've done a lot of work for the government. Next slide. One particular base was again at the Fort Sill. So this, kind of getting near the end, a little bit to go. But battery storage, again, the pricing's coming down. So you see it continues to come down, kind of like solar panels. The price of solar panels came down. And that just helps these options with renewables. Because again, if you have renewables, and the clouds come by, you need something to offset those renewables if you're committing to more and more renewables. And again, by committing to renewables, though, that's reducing your carbon footprint. You're addressing climate change. But now you need other things to because of that benefit. There's always something that maybe offsets a benefit that requires some other something to support that. So next slide. Yeah, and this shows just an example of the different technologies, different types of batteries. There's ramp rate, which is again the idea of how fast are you going to discharge. You're going to discharge every minute and charge like very quickly, or are you going to train the batteries for 3 hours and then charge them back up? And then there's the storage capacity. There's bulk storage. So there's lots of applications. You see the frequency regulation. That's one item. The other green box is the area where you're kind of balancing out the renewables out there. So there's lots of work, again, being done on batteries. Next slide. Yeah, this again shows lithium-ion, sodium-sulfur, advanced lead-acid flow batteries. They're good in different. They each have favorable, average, unfavorable, characteristics. And again, you could download the presentation or watch the video again later, but it's probably better download the presentation so you can read the details of the different battery technologies that are out there. And this is also, keep in mind, an opportunity like MIT's doing. If you have an electrical engineering department, it's a good area to maybe do some testing. I graduated from Drexel in 1976. That was the first energy crisis under Jimmy Carter. And I was actually involved in a project. I designed a little control system that measured the amount of power current flowing, how much the batteries were charging and discharging. But we actually put a small windmill on a professor's roof. It was a funded, a research funded. We had batteries. So this was in 1976. But it was interesting what you can learn once you're actually implementing those systems. But that energy crisis went away, but now we're in kind of a more real situation with the climate issues. That back then, that was only because of the Arab oil embargo. It had nothing to do with climate change. That energy crisis in the 70s. Next slide. Yeah. So again, this is some more details on lithium, sodium sulfur advanced flow batteries are basically where you've got a tank of chemicals that are now storing the charge for you. We just did a feasibility study with one of the universities in Pittsburgh, and one of the things they wanted to know is which type of battery technology would best work at their site to complement some solar they want to put in, and actually in that case, the university is partnering with the local electric utility. So there's lots of opportunities to partner. So the university is not, that was where we did a nice feasibility study, and now we're writing the specifications up for a installation of some solar controller to integrate the solar with the existing generators and integrating with all those existing generators, which is tricky because you're integrating with different manufacturers' equipment. But there's lots of opportunities to partner. Next slide. Yeah, and this just shows some examples of battery monitoring. You do have to monitor batteries. And this is why you have to look at the applications. There's a thing called runaway, where a battery starts to heat up inside. And some of you have seen where they're those little scooters, those things the young kids are buying. They stand on them and they lean forward. So if you short out a battery, it's gonna keep getting hot, and kind of melt down. So you need to monitor batteries. And again, there's lots of technology out there that takes care of that. But it's just something you can't forget about. Next slide. Yeah, and then next slide. So this just kind of talks briefly about different options. You do have solar, you've got heat pumps, you've got chillers, you've got CHP, you've got wind, so energy storage. So there's lots of different systems, and you can, one concept is not only share electricity, but is there opportunities to share hot water, chilled water, those type of things between multiple sites. So we're just on the cusp of this whole resiliency microgrid. It doesn't look like we're going to go back and build any more large generating plants. So we're really, in a sense, have to figure out how to do this locally, within our own little community or within our own little university. And the fact that those large plants aren't being built changes the whole orientation of the grid, because keep in mind the grid was designed send power, over these lines, maybe 3, 4, 5, 20, 30 miles. Now it's all going to be generated locally, so the controls, everything's going to need a whole slow process of engineering, design, and changes. Next slide. Yeah, and then the feasibility study. This is one area to consider. Now, obviously, you don't want to be upgrading your system if it's not working properly now. So, you want to have a safe and efficient electrical distribution system. There's a item called arc flash, which is, most of you may be aware of it, but there's new regulations out now that require when someone's standing in front of a large electrical panel, a certain amount of energy that can come out of that panel should there be a short circuit. So people need to be wearing the proper protective clothing. So what we do is we go in and do a study and tell you, okay, and each panel gets a label. And when someone's standing in front of the panel, if this says you're okay with just safety glasses, that's fine. But if it says level 4, you better have a lot more fire retardant clothing on yourself. So things like arc flashes, if you have circuit breakers tripping that shouldn't trip, you may need a study, or you may need to upgrade the trip systems. So you do want to take a step back and don't spend money adding things and then you have something fail. There was one university where we did a power system study, and here they added a whole new wing, right? So they add a whole new wing, and when you looked at the single line diagram, they tapped off an existing feeder in a manhole that wasn't heavily loaded and brought that over. Now, the consultant who did their job, now remember, the consultant's job was to add the wing. So since they tapped off that feeder, and now you had two main feeders coming off the original one circuit breaker, they added their own circuit breaker, which is per the code. So in other words, if you have one circuit breaker feeding two main sources, they need to have their own protection, because you don't want the main circuit breaker tripping and then you lose everything. So they did what they were paid to do. They added a circuit breaker to this line for the whole new wing. But what was still on the old line was a 35-year-old transformer. But their job wasn't to go back, their scope of work include fix anything else that's impacted by the power distribution addition for the new wing. So basically the 35-year-old transformer fails, which, it's a 35-year-old transformer. It trips that main circuit breaker that shuts down the whole new wing. So you have a person standing in front of an administrator trying to explain, which you can understand an administrator not really liking the answer, that you're telling me the system was designed so a 35-year-old transformer sitting way over there, behind bushes, caused our new wing to go down. But by doing a study, by having someone step back and do a study of your whole system, it identifies those kinds of things. It wasn't a difficult fix. They had to replace the transformer, which they did on an emergency basis, but we said, no, you need to add its own circuit breaker there now, or fuse disconnect switch, so that if that transformer fails in the future, that device opens and you're not tripping the whole facility. But the whole idea, too, if you go to the second row, everybody should be able to handle a 1-hour outage, maybe a 1-day outage. But what's happening with storms and the whole issue with resiliency is, with the Sandy storms and different things happening, people are seeing 1-week and 2-week outages. Now, that's a whole different space. For instance, in Pittsburgh, the universities and the hospitals realized that after about 3 or 4 days, the city does not have the infrastructure to deliver fuel oil to everybody who's going to need fuel oil. So, hopefully you're going to get it, but if there's a hospital nearby, they're going to get it, or a police station or fire station nearby, they're going to get it. So people are starting to realize that, you may have a day tank for oil. Well, and you can keep filling it every day, but that's assuming no one else, not everybody else in town needs oil, because most cities do not have the infrastructure to deliver oil. There's just not as many oil trucks. It's not a business that warrants all that infrastructure. So you need to look at, and the idea is you come down the next line, you've got transfer schemes, tie lines, added generation or upgrading generation, maybe doing a microgrid. But the recommendation that comes out of this slide is to maybe start planning things. Saying to yourself, okay, over the next 12 to 24 months, we want to beef up we want to make sure our electrical system's in solid order, but we want to make sure we can handle a day outage. And in 24 to 36 weeks, we want to be set up resiliency to the point where we can handle a 1-week outage, and maybe 4 or 5 years out we will grow to being able to say we can go even beyond 1 week. So the idea is you got to plan this. It's not something you're going to find money for overnight. Next slide. Yeah, so this just shows, microgrid solution. You could do feasibility studies. You can have service contracts to maintain things. You may need batteries. You might need fuel cells, distributed generation. But again, the upper right shows, it's that control. That's the heart of the system. Next slide. Yeah, and then next slide. So this just shows some resources. So again, if you go to eaton.com/microgrid, you could watch the PGE video. It's a very good video. And then the Eaton video, what it does is it shows the microgrid that we put in at the Fort Sill Army Base. Now the PG&E video is not an Eaton video. It mentions Eaton at the end because we were one of their partners, but it's basically their video promoting their community microgrid. Now what they don't show you in that video though is, if you recall, I showed you a single line, a transmission line showing all those customers connected. You'll hear, an interview with the person at the kettle plant. You'll hear a local resident talk about their hot water heater. But the slide deck here is giving you more detail than what's in the video. The video is a nice advertising video, and these other documents are there on the. And a presentation similar to this one should be on there too. But you see there's an MIT report, there's energy storage documentation, lots of different available information. And again, maybe Second Nature can either link to this or figure out a way to link directly to the PGE video. Next slide. Yeah, so again, this is, Eaton provides lots of services, microgrids part of it, everything from studies, engineering, upgrading electrical equipment. Next slide. So that pretty much leaves us with some time for questions.
Great, thanks so much for the presentation. And just to repeat that these slides will be available. We will distribute them to registrants, and then you can also watch the presentation on YouTube. We'll share that link. So we have a lot of questions from the the registration survey. So I think we can start with this one, which so how can campuses in higher education partner with their local community to enhance resilient energy design?
Yeah, but what I would suggest is, obviously if there's a state-funded program, but I would suggest just calling a meeting, reaching out to those other large whether they're large institutions or schools, talk to their energy manager, their plant engineer, and maybe just have a meeting where you all meet together, in one of your locations and just discuss, if nothing else, what generating sources do each of you have, and are some of them old or some of them new, and just that would be the start, to talk through with your partners in the community, and again, if you want, you could show them that one slide where, if you watch the video from Portland General Electric, you don't see that slide where it shows the interconnect of different local people to build up the resiliency, actually using each other's assets if needed. So I would start off with a meeting. Now again, some states have programs that help you get started. But that's what I would highly recommend. And I think if you get the right people, again, it would either be the energy manager, the plant engineer, it could be somebody even higher, a director of maintenance or of facilities. It might even, so that's what I would recommend, try to have a meeting.
Great. And we had several different questions sort of on the theme of decarbonization. So, how can a campus develop a resilient heating and cooling system that doesn't rely on external natural gas supplies?
Yeah, that's a very good question. Right now, specifically for heating and cooling, okay, because that's energy. I mean, that's you're either you're cooling or you're heating. So energy is neither created. Energy just changes. So you have to get that energy from somewhere, right? So you can add renewable energy, but then if you're going to want to have some battery storage, because if you're relying on those renewables, whether they're solar, primarily I assume would be solar. It's difficult to put a windmill anywhere. But if you beefed up solar, okay, and you'd want to do this primarily too if you had some state, some some incentives. And then you would add the batteries. Now, the only problem though is with heating and cooling, it requires a lot of energy. So there's really economically, you know, a lot of people are shifting from, say, fuel oil to natural gas. Even if you put a fuel cell in there, that's burning some sort of gas. Sometimes it's hydrogen, sometimes it's natural gas. So the only way to truly, it would be to slowly migrate towards, you know, solar with battery storage, because if solar is becoming a bigger piece of your generation source, you can't have, you know, cloud cover for 20 minutes that, you know, all of a sudden you lose everything. But see, even in that case, most people do not put in solar beyond maybe 20% of their load, only because you can get 3 days of cloudy days. So, you know, if it's only 20%, so people still obviously stay connected to the grid in those cases. So I'd say right now there's not a lot of technology that gives us options because of the energy needed from either, you know, literally burning hydrogen or burning, you know, fuel, or buying electricity, which again, you know, when you buy electricity, the utilities are burning something, or they're using nuclear. And I worked at a nuclear plant when I was in college. They, you know, they are green, even though you know, there people are concerned about them. But it's a shame those accidents occurred, because they actually were a good alternative to climate change if we didn't have the other issues with them.
Mm-hmm. There were some similar questions about renewable energy. Is there anything else that you'd like to add beyond the answer to the last question about how renewables can play a role in resilient energy systems?
Yeah, yeah. I mean, so renewables are definitely key. Now, you do need, you know, you do need roof space, or you need a field. You know, you do need to do 1 megawatts to generate 1 megawatt of power. You need about 7 acres. So that could be a field that no one uses anymore. Those types of situations. What the government is now doing is they're allowing people to come in, put solar panels on their property, and as long as they have access to that property, the majority of that power flows to the actual customer. Now, you have to be literally next to an Army base, so they're being very flexible. So renewables are key, but again, they can only be a certain percentage of your total load, only because they're not as reliable as a gas generator. And in general, people are finding that the gas supply is more reliable than the electric supply, because the gas is coming from a plant that, you know, has gas coming to it to feed its electrical needs. So renewables are key, but it's going to be a slow process. You know, you can't, right now you really shouldn't go above 10 to 20% of your total load, only because it's just not reliable enough because of, you know, the weather situations. But there's, you know, fuel cells out there that might improve, that do make use of gas, but maybe won't burn as much gas as a, you know, CHP unit burning natural gas.
In terms of thresholds for, you know, cost savings or demand loads, are there any considerations that you should think about in terms of thresholds for whether or not a microgrid is viable?
Yeah, that's a really good question. There's companies right now that are offering to, in New York City, for an example, there's companies going into buildings and saying to the building, give us that space in the basement that you can't rent. You know, it's sitting next to your big air conditioning compressors, and what we're going to put in that little corner is battery storage. And what we're going to do with that battery storage is we're going to help you shave your peak demand. So basically, we're going to store the battery, you know, charge the batteries at night, and then during the day, when your time of use bill is high, we're going to clip that off and drain the batteries. And they're saying, some of these companies are actually saying to the end users, you know, we'll install the system for free and split the savings with you. Now, what that means is if you have the money to put the battery system in, you're gonna earn all those savings, you know, rather than share. But I mean, somebody offering to do it for you now, it's kind of like a venture capitalist. But what it shows is there's definitely money to be saved in peak shaving. the fact that these 2 or 3 small companies have been able to raise, like a couple $1 million for this venture, the people they're presenting their case to that they're getting the money from to start these businesses, they've got to be showing them some numbers that are, exciting to an investor. So there's definitely potential, and again, the battery storage now, keep in mind, you can put battery storage in regardless of renewables. You just put battery storage in to help with the peak shaving. And again, you want the controls and the whole system to integrate with your other potential generation sources. So that's definitely a growing area, and again, what's helping that is the lowering of the battery cost, because that's one of the assets you're putting in. But so that's definitely a good question, and something is starting to move forward on its own.
Mm-hmm. I think we have time for a couple more of the questions. So there were a few that were just about general barriers facing some of these technologies. What are some of the common things that you encounter?
Yeah, there is definitely some barriers from the standpoint. One piece is the regulation, the utility regulation piece. See, now, utilities, with the deregulation of utilities, a lot of them cannot own a generation asset. So they own the transmission lines, but they don't own they don't own the power plants anymore. And that was to kind of make things more competitive, so more people can generate power. But the problem with the utilities is, now this is why New York is doing this with the utility. Basically, the state is saying to the utilities in New York State, you need to let a university generate power from their generators, that when they don't need that power, sell it back to the grid, and they need to earn money to make that financially viable for them. Now here you are, the utility. That means you're going to pay the university money. You're not going to sell them your own power, because they're going to generate their own power and plus sell it to one of your other customers. So the challenge right now is, and they're trying to make sure they make the utilities whole, because if the utilities see this as a threat, what they put up barriers, and this has happened in the past, where, to give you an example, in New York City, there's 4 high-rise apartments. 3,500 people live in these apartments. 3,500 individual apartments in this 4-building complex. They disconnected from the utility 10 years ago because they had their own generators already for their 4 buildings. They disconnected from the utility because the connection charge was so high. This cost to just be connected. So that's what they're trying to do away with. So those regulations are coming. They're not going to let. But I have to be honest with you. The one, when you look at the finances, if you look globally, we here in the U.S. pay the lowest for electricity than anywhere else. And again, I don't work for a utility, so there's no benefit to me. I don't want my rates to go up either. But the simple way to do it is if rates went up higher, because now the utility doesn't have to, lose its infrastructure and its people, but still has enough money to pay different people who want to generate and feed into the grid. So my prediction is, one way that will make it work is if we all just paid 10% more in our utility bill, and now that 10%, and by the way, some states already do this. In other words, like in New York State, they gave out $100,000 to 83 different communities. That's $830,000. They're going to be funding 5 projects, I think it is, up to $1 million, and another few. So all that money is coming out of a fund where they say to the utilities, you got to charge a little extra, and you got to send that money to us in the state, because we want to implement programs that build resiliency. So that's basically, everybody in New York State is paying more money. Now that money is flowing back to the communities through these free feasibility studies for worth $100,000 each. But I think the reality is that's the one thing that'll get the ball moving.
Great. Well, thanks so much for your presentation and answering questions. We have to wrap up at this time, so I just wanted to say thank you again for everyone who was attending, and please send us any additional questions you might have, and we look forward to distributing the email and the slides and the recording of this session in the future. So thank you again.
Thank you. Bye now.